So yesterday's talk was about economic geology, and I was just trying to go through some of the fundamental ideas about economic geology. Just as a review, the fact that the concept of ore is closely tied to economics. The idea of mineral systems, how we're trying to simplify our task. We're trying to integrate a lot of characteristics about unique deposits, coming up with a synthesized understanding about these types of deposits, and that's our mineral system, so that's quite important. And then I went through the basics about how to document these ore deposits in terms of their rock types, structures, veins, alteration minerals, and how that's important in terms of developing a list of data that you can then interpret. And then I wrapped things up yesterday by producing a genetic model. Remember that block diagram? So those are the main things of yesterday. So what I've got installed today is more about the applied methods of how do you actually go about examining deposits. So what I'm going to do is I'm going to go through it step by step and give examples of past areas that I've been to. So today it's all about mapping, logging core, and sampling, and I'll touch on some advanced tools. As I mentioned yesterday, there's a list as long as my arm of advanced tools that I could talk about, but I'll just mention a couple just to give you a bit of an insight of all the interesting things that we can do with these rocks once we've collected them. So any questions from yesterday? Everyone's pretty happy with it? I'd also make a note that basically I could give this talk to just about anyone, and I have given it to just about anyone. I've given it to third years. I've given it to a team of Iraqis who visited Perth a couple of years ago. When I gave it to them, there was a translator next to me, so I'd talk for about 10 seconds and then I'd stop and the translator would interpret that to the Iraqis. This, I think, hopefully you can draw upon in subsequent years. If you stay with geology, this will hopefully be useful when you go to Kalgoorlie into the field and then you actually apply these things. This will be stuff that you'll be doing. So if you stay with us and you go off to Kalgoorlie, you go, well, right, you guys, the task for today is mapping this part of the pit. How are you going to do that? And while one group does that, the other group will be logging core. So I think hopefully you hang on to these presentations and you can actually apply it, and that's really the best way to learn. So today I'm just happy for you to try to take it in, understand what I'm talking about, the general aspects, but you won't really have a firm grasp of it, and I don't expect you to do so, until you're actually in the field and we're with you and you put it into practice and you work out what works and what doesn't work. Okay, with that in mind, let's begin. So let me read like that. So preparing geological maps. It's the first phase of exploration. Basically, it's the cheapest way to gather a lot of data very quickly. So instead of just drilling randomly, which you wouldn't do, it's easier to have a team of geologists and given a task to work out to test our hypothesis. Remember, all scientists, we have a rough idea of what we're expecting in this area. So let's go out and do some mapping and how we're going to test this hypothesis. So these are the things that you work out and then you apply in the field. So again, it's important to separate factual information from interpretation. So we're going to gather information about our rock types, structure, etc., what I talked about yesterday. And we're going to do it in a way that afterwards we can actually interpret it. Not only can we give it to people who haven't been there before and explain it to them very simply, but maybe a year later or 2 years later, you actually go to this data again and you'll have to read it and understand it. And unfortunately that's what I do all the time. I'm doing things in parallel, so I have to refer to field notes from 2 years ago or 5 years ago, which is quite painful if you're there and your writing's messy. At the time, your care factor was down. But in a year later, this is really vital. So it's really important to get this data. Even if you're working within a company, you do have the filing cabinet. You'll go through it and you'll gather this information, and if it's recorded in a proper way, you should be able to go back, and you're not starting from square one each time you're doing a job. So I'm going to talk about how to develop these maps in a practical way. And I'll talk about the examples of mapping outcrop. You're just walking out in the field along a ridge, but also how do you map within a pit, how do you map underground, and what do you do with the drill core. And then I'll talk a little bit about sampling during these processes. So this is an example of field mapping. So I think yesterday I probably will show similar slides, so you should be familiar with some of them. And so this is an example in Korea, Sokjun, Songtaek. We're out mapping this bit of outcrop, laying down a grid, a metre grid, and then on my graph paper, that's the scale there, 1 by 1. So what I'll be talking about is fundamental methods today. And I won't really talk too much about the technology, because the technology is useless unless you have a firm idea of what you're doing. So I think with everything, the first step is reconnaissance. So whether you're mapping out in the field or in a pit, or even if you're logging drill core, it's basically the first step is get an overview. Because I've been caught out in the past where I've say, looked at a bit of drill core, and I spent half my time on the first couple of metres, whereas I had like 200 or 300 metres beyond there. So what I like to reinforce is that it's better to spend the first hour, just walk down the drill core and up again. And if you're not walking, it's not reconnaissance. So you're just naturally drawn to interesting things in the drill core, and you sort of get sucked there, and you start looking things, pick it up, and then before you know it, 30 minutes have gone past. So if you're not walking, it's not reconnaissance. The same thing applies if you're out in the field. Drive around the area that has to be mapped. So at least in your mind, you know what 5 kilometres looks like. If you're in the pit, walk up and down. Whereas the complexity is that in this one corner of the pit, and then everything else seems to be quite simple. You know, this is going to help you to work out what you're going to be doing for the remaining 95% of your time there. So that's very important, the reconnaissance step. And so based on that, you develop a plan for an area. Whereabouts are you going to spend your time? In this case here, there's 2 different areas. You know, my master's student, Jenny Dickinson, was down there in the swamp, whereas Brad McKinley was up high. They had the same goal, but they had very different areas to deal with. So the logistics were very, very different. So in the case of Brad, it was more about walking along the ridges. For Jenny, it was probably working out transects across this area to do it in an efficient manner. So walking up riverbeds, along ridges, that type of thing. All of that can be worked out in the first couple of days during the reconnaissance. So based on that, we have to work out, this is quite important, what scale are we going to map at? Are we going to choose a scale which is so detailed that we're going to consume all our time just in the first little area? Or are we going to choose a scale which is so huge that to get all the important information, it's impossible to do it on your map. So you have to work out what scale to work at. So how do you choose that? Well, basically, how much time do you have? You know, is it just like a week or a day? That type of thing. How complex is the geology? Is it dead simple, or do you think it's going to be quite a complicated situation? And how much data needs to be collected to resolve your hypothesis? I could collect a lot of structural data for an area, and it could be wasted. I could just collect all the bedding data, but if it's not going to tell me about what's controlling mineralisation, then that's not very efficient. So basically, when you do your field work, you have this framework in your heads. Right, I've done this before, I'm going to follow this method, but no 2 areas are exactly the same, so you always have to juggle these differences. okay, and about geological mapping. It's about taking this framework into the field and assessing the situation and working out what's important to resolve your question. When I was a PhD student, there was was it the Anaconda company method for mapping. I think it was the flavour of the month back then. But what was so useful about it was a graphical way to map. So it was a guy introduced by an Audi, and it's a way to show these different features on a base map. And it's effective to use symbols and colour, but what I show here, this is basically his example of the methods. I'm just showing, obviously, in black and white. And I guess the point of this is just to show that even with the limitations of not showing colour, you can still create a map which is quite clear and powerful. So what this is showing, again, out here, the scale and the north arrow and the legend, what's so good about this is that he's mapping a rock face. So here's the contact there, this is the air side, and this is the rock side. And then he's separated the rock types on this side here. So this is a code, this is, I don't know, granite, doesn't really matter too much for today's purposes. So different rock types here. And then he's showing some structure as well, some contacts. And then on the air side, he's showing these different symbols which relate to alteration minerals. So he's got alteration in the mafic rocks and alteration in the feldspars. And so you can, I think what is so beautiful about this is it's so simple. So later on you can give this to any geologist and then they can look at these patterns and then they can start drawing an interpretation. This is factual information that anyone back from 99 to now can come up with their own interpretation. So this is a really nice way, and I think this is what I'd encourage you guys to do in the field. This is probably be your first task in the field to create something like that in a pit. So this is a way to do this on one piece of paper. The alternative is GIS methods. Can anyone tell me what GIS stands for?
Geographic Information System.
Yep, that's right. Hands up. Has everyone heard that before? Has anyone heard that before? Apart from you? Yep, only 2 people. Okay, so what it all is a mapping method. Essentially, it's in a computer essentially. So. It's basically taking separate data sets and putting it within a program so that you can turn things on and off. And once you've got these data sets in there, you can then query it and you can apply statistical methods to it if you wanted to. You can do it in geology, you can do it in geography. So it's very common these days, and I recommend if you guys go into doing geology, do that as a little unit. So what this is, we use a program called ArcGIS, and in that program, I've got a screenshot here. I put on a layer, and that base layer can be topography, or it can be an ortho photo, an aerial photo, like I've got here, and then I switch on a layer for, topography. This is an aerial photo. I've got some roads to get in there, and I create a base map. So this is how I orient myself in the field. So imagine me with an A3 clipboard. I've got this stapled down essentially, and now I'm about to begin mapping. So what I did a couple of years ago, I had that as a base map to find myself, and then I cut out some transparency, stapled that on, and I put my rock types on top of that one. Then I got some more transparency, put a bit more on, and just did structure. And then another one as well for alteration. So I had all of these layers, which is like a pseudo GIS type of environment. And that was a great way to record a lot of data without having that complexity. It was a lot easier to do that rather than the Inaudi method from previously. What was annoying about that was that I had to take paper out. It was a fixed scale, so I had to choose an appropriate scale at the very start. And then I had all these pieces of paper flapping in the wind for a couple of weeks, which annoyed me a lot. So, but basically these are the fundamentals, and this is what you'll be doing in second or third year. In tandem with a A3 clipboard, I have a field notebook. And so what I can't fit on the clipboard, I put in my field notebook. There's no point cluttering this with lots of text and words when I can just have it in a little notebook. So that's what I did. I had that in tandem. And then apart from making notes, I also made sketches of field outcrop. That's about 1 metre, 3 metres. And then as I came up with an idea, I came up against a really interesting cross-section exposure. I drew something like that. So it was a very nice way to integrate the clipboard and the field notes. But what we can do these days is we can take a tablet out. So about 2 years ago, I got my hands on a ruggedized tablet PC. It's waterproof. It's got a built-in GPS. I've also got a GPS about that size, and I just put that on top of my mapping vest or on my backpack, and they talk to each other. So I can walk in the field, and I don't have to worry so much about reading off a hand GPS and then plotting X, Y, and finding myself on the map. So that was an advantage. And it's also multi-scale. I can zoom in if I want to, whereas with the paper you just fix at that constant scale. I also, yesterday I talked about the boundary mapping technique, which is basically putting pen on paper and you see that you've got a rock contact, so draw it on your map, rather than the point technique, which is like I'm at station 1, take the information, go to station 2, and I don't do anything else. It's in a spreadsheet. I have no sort of spatial idea of what's happening with my map. So I'm strongly in favour of the former, which is the boundary mapping technique. But lately I've been developing the use of creating a spreadsheet. So I go in the field and I work out that there's certain parameters that I definitely want. I want to know my location. Basically I'm picking up a rock. I want to record where that rock was taken from, the XYZ coordinates. And I want to know basic things about what rock type it was. I record structural information, record things about the alteration intensity. So I developed a table, because you're out there, you're a bit tired, you're hot, you're thinking of home, all these things, so you forget to record these important bits of information. So these days I go in the field with my tablet and I flick between windows and I fill out this spreadsheet as well. And then I can plot it in ArcGIS afterwards. So these are my station numbers. This is about 8 kilometres. Here's my bandar information outcrop, and each one is a station. And I'm recording factual information. I'm picking up a rock, looking at outcrop, and this is factual data. And the beauty of that is that I can come back later on and I can plot up this data from an Excel spreadsheet in ArcGIS. And I can plot these different quantities, and then I can show them symbolically. So if I just pick out, say, this blue one, this is the average band thickness in a BIF, in a bandar information. So you can see quickly that the band thickness gets really small over the ore body, and then you have these thick bands in distal areas. If you look at these, which are the percentage of alteration minerals, obviously there's more alteration minerals over the ore body compared with the distal areas. So I wasn't influenced by that. I wasn't out there mapping, colouring things in. I was actually recording things as I went along, and then later on I plotted these things up in ArcGIS. So my message is that my technique is evolving. I think what I did 10 years ago is fundamentally similar, but I've just taken hold of different ideas, different bits of technology. The panacea is not new technology. It's actually a bit of a danger because you think that you're ahead of the game because of this new tablet that I've got. So it's important to apply these fundamentals and then just be receptive to new techniques, new technology. This is a capture from the Midland Valley website, so a bit of text here. And what I'm showing is this is a program called Field Move, which I use these days. And it's a very simplified, broken down version of ArcGIS, which has all the bells and whistles and statistical manipulations. You don't need that in the field. You just want a simple screen, put in a contact. You want to have a list of symbols and then put it in and then move on. So this is what I use these days. So that's mapping in the field. Mapping in open pits is very similar. The same methods are applied. However, we've got the advantage of existing data sets. So basically, you get into the pit, they've been digging there for years already. And they've been collecting existing mapping, the mine geos are mapping, but also they are drill and blasting. Each time they drill, I mean, they've got a sample, so they analyse it, or they, at the very least, record the rock type. So my message is that in the mine environment, you've just got a large resource of existing data that you can have access to and incorporate it into your interpretation. And we've also got the added value of a little bit more 3D because we're actually going into a hole in the ground so we can map cross-sections as well as the pit floor that we're walking on. So this is an example from Canada. It's an open pit. I didn't put on the pit outline here for some reason. This is for a publication, but basically where I got the data, that's the pit wall. So as you can see, there's nothing much different about this pit map compared with a regional map. The only difference is essentially this is 100% exposure. Obviously it's a couple of 100 metres down. The only difficulty is that the trucks move up and down and disturb the soil, the dirt a little bit. But we have the advantage that every 20 metres there's a little drill hole. So you get that data and then you can mark out these contacts very accurately. So in the previous example I showed rock types. Here I'm showing my alteration map. I showed this slide yesterday. But then I've got the advantage of bringing in geochemistry. So these drill rigs have drilled the holes, geos have come along and sampled it, and then they have basic element data, so gold and copper. And so there's a lot of point data here, and then you can contour it, and then you can come up with a nice hot-cold map, which is contoured data essentially. So here I'm showing one level in the pit at this constant relative level for gold and with copper. So where you have most of the gold, you have most of the copper. It's a porphyry copper gold deposit. So the fluids are introduced with the felsic intrusion and dumped out the gold and copper. And then what's interesting is that in this area here, as you go deeper, what's that, 30 metres deeper, there's a big hole in the ore body. Have mineralisation of gold either side of it, also with the copper. So basically there's some faults there. Yesterday I showed some vertical offset in a cross-section at this one deposit. We've got the same thing. There's different blocks and they've just sort of fallen. And so these are different levels of the deposit. And so we're juxtaposing mineralised areas with a deeper unmineralised area of the deposit. So, and that was unusual. Didn't know that until got the data plotted up. Now, why is that the case? Oh, I mapped these faults there. Oh, what do you know? They're actually sort of marking the boundaries, so it makes sense. Look at these faults. Oh, there's normal movement. This is up versus down. These things piece together and you get quite a nice interpretation. The next thing is, I think, quite exciting, the use of drone technology. And basically, we're on the cusp of this technology. So who knows where it's going to lead. If real estate agents are using drones to survey mansions from the air and post that to the potential clients, why aren't geologists using drones for their field exercises? And that's what has been started, and there's many advantages of it. Here's an example of the octocopter with a camera pointed down, and here the SLR is just pointed at the rock face, the vertical rock face. The advantage is that you collect the digital images from outcrop and surfaces. It's very fast. It just whizzes around. It's automated, so you can program it to go over a certain area. Check out the resolution. 1 pixel is a centimetre. And the accuracy is on a millimetre. So not only can we get these high resolution photos that you can just zoom in and more than you probably need, but we know exactly where this data is from, down to the millimetre. It's awesome. So we can gather the data very quickly, efficiently, and cost-effective, and it gets us to places that we can't really sometimes get to. Imagine a unstable pit face wall. So Steve Micklethwaite has this example from Tasmania where there's some beach outcrop. I think the water is down here. It's been clipped so you don't see it, but he's sent the octocopter up and down, I think collected over less than 30 minutes or so. That data produces a seamless map. And then because you've got the Z coordinates, you can produce a point cloud, so you can spin that around and you see the elevation, digital elevation, so you can see here this is a bit higher, down near the shore it's a bit lower. And then you can also put it through another program which will map out boundaries. So it's automatic and edge detection, and so you're marking out these major faults in these areas. And not only that, not only does it detect them, but you can get some orientations from them as well. So you can get this very, very quickly. So, and in many environments. So to my knowledge, Rio Tinto are using this to survey their stockpiles. So how much ore do we have, how much waste. They can just quickly, they use a drone to go up and down and quickly gather this information on a daily basis. To my knowledge, I don't know if anyone's using it in the pit, but I think it's got great advantages. Each day you can just send it out. At the very least, record images. You know, just based on colour, you can map out BIF versus non-BIF in the pit floor, but also in the face. It's another advantage for pit mapping. And then what happens if we strapped, say, a spectrometer to it? I'll talk about this in a few slides. We can record that information as well. Why is that important? Well, I'll talk about that in a few minutes. In the last few years, I think about 10 years ago, I had a chat with a guy in Canada and he said, oh, look what I've got. I opened up the briefcase and he had a $5,000 SLR camera, digital camera. 10 years ago, I guess it was quite a fancy thing. What he was doing was he was taking photos of the pit wall, and then from a slightly different point of view, from here and then from there, for two different angles to get the stereoscopic vision. And then he can then put that in a program, and so he can see his whole pit in 3, spin it around. Why is that useful? Well, again, quite often you can't get to different parts of the pit. When I was a student, I was basically could go anywhere. Oh, there's a pit floor, there are these berms, which are to stop material raining down. I could walk along the berms, no worries. And then I've seen things evolve over time. Structural engineers, oh, do you really need to go to the face there? Well, yes, my job is at the face. I need to actually put my hands on the rock. Oh, we'd rather not. It's getting to the point where they'd actually like to have no one in the pit. So I think this is probably steps in the future. But even now, it's useful for us because we can record this information, see it in 3D. We can get structural measurements from these pits, which is awesome. Not only at the floor, but also higher up the face. So I think it's exciting. I think these are tools. They're not the solution, and we're not doing ourselves out of a job in the future. We need these fundamental ideas and knowledge on the data. What are the limitations? How's the data recorded? There is a need for a geologist. We're not going to have driverless people, trucks. The geologist is not going to be removed from this setup. Okay, so mapping the pit, mapping underground. Not only do we have the rocks at our feet, at our sides, but we've got the rocks above us as well. In every direction, we're surrounded by rocks. Isn't that nice? So we can map these. We can use it to our advantage. And the clear advantage is that we're now mapping the roof, which we call the backs. And in fact, that's where the valuable information is because, again, the floor is dirty, the sides are very beneficial, but the backs are cool. So this is in Korea, and this is a epithermal gold vein that we're mapping, and that's the map from it. So the scale here is about, 30 metres. This scale here, I don't have a scale bar, but I've got a grid on it, and that's about 100 metres, so it's quite a big difference. And so showing different rock types, komatiite in purple, felsic rocks in other colours, and I show the ore shell in this line here. So and in red, you can't see it so well because of the brightness of the room, but the ore zones are here in red, and then the larger disseminated ore body is covering it. So this is basically how we map underground. Logging drill holes are, let's see, it's a continuous sampling of the stratigraphy. So even when we're mapping, we're just seeing the exposed area. So wouldn't it be nice to have an access right through an ore body? How do we get continuous access right through an ore body? Well, we drill it. So there's different types of drilling, and you can see the increase in cost. The cheapest is just to get back little bits of rocks and powder, called RAB and RC, both providing little fragments. So structure is not really recorded, so how do you record a vein measurement if it comes back in pieces? So the more informative form is diamond drilling, so it comes back as core, essentially. And so we can map out rock types, alteration, structures, and we sample it for geochemistry as well. And this is an example in the field, so I'm still going out there these days with paper and pen if it's raining, if I don't want to be 100% reliant on a computer. You know, sometimes it runs out of battery, what are you going to do if that happens? So I always plan for plan B. So this is a dirty log. Again, over many years, I've developed a logging sheet, which I'm happy with. This logging sheet is commodity specific. So in this case, I'm looking at a volcanic hosted massive sulfide deposit. So, you know, black smoker, you've probably seen it in documentaries. This little black smoker on the bottom of the ocean bed releases the smoke, deposits out the minerals. We're looking at these ancient ore bodies like that. So it made sense to emphasise certain things like structure and rock types and alteration minerals. If I'm doing iron ore, I change the framework a little bit. But you can see, generally I have depth down the hole, lithology, which is a rock type, have different textures, structures that I'm recording, weathering, intensity, and alteration minerals, some geochemistry, and some comments. The company these days likes to do things basically in a spreadsheet, but what we're encouraging is to do a graphic log. This is a graphic log for obvious reasons. If I were to replace this with just numbers, you can't easily compare this interval with that interval and that interval. In one glance, you can see it increases, does a little wiggly, and then decreases. Imagine if I replace the alteration intensity with a percentage. You just can't see that. So if you do become a geologist and get employment, you will have to do that because the company wants you to do it a certain way, and you'll have to record this data, which will then be part of their database, which will then be put into 3D, etc. But what I encourage is that every now and again, do a graphic log. If you log 100 holes, do one graphic log. You'll learn more from that graphic log than you did with all these routine logging for the company. So polishing it up, this is just cosmetic. It's the same data, but I just did it in CorelDRAW. Took me about 2-3 days of solid digitizing and making it picture perfect. And these days, what I can do, what I haven't shown you here, is I can actually have a program which will do this automatically for me. So I can, as I log the hole, I can put it into the PC, and then I finish logging, and then I've got something pretty much that quality. And another example from the porphyry deposit. So slightly different from the one before, and that's the main point. Still a graphic log, same sort of template, but slightly different parameters there. Can't see this very well because of the light, but the main purpose is just to mention that, well, this is a two-dimensional portrayal of what's down the hole. And we know its position in space at the top because we've started drill at this point here. We've got our GPS. We put down this tube, say halfway down the hole, and it records its XYZ coordinate. And then we put that tube down at the base of the hole. So we know where that hole is in space. And so then we can then put it into a program and we can show that one drill hole in 3D. We can look at it from any view. If you do it with one hole, do it with all the holes, and then you can link things up. If we've got the geochemistry, we can then make contours, and we can get the computer to do that by statistical methods. So within about half a day, you can put all this data together, let the program do its statistical job, and then you can come up with some ore shells like this. So this is copper. I've got banded iron formation here, and I've just got the copper values. Sulfur is a little bit wider. MgO, magnesium, is a broad halo, and indium is also a broad halo as well. So it's a very quick and efficient way to do things. So for the last couple of minutes, this is the spectral data. I'm just going to whiz through this. There's a lot of detail here. I'm just going to crystallize it into the main things. So I mentioned with the octocopter, why not have a spectrometer attached to it? What is a spectrometer? It's just recording spectral data, a spectrum. So in very simple terms, the sun hits the outcrop and things are absorbed by the rocks, other things are reflected. That's why we can see it. Our eye is essentially a spectrometer. Things are reflected off the rock, we can see it, we can see the different shades in colour, which equates to minerals, doesn't it? Chlorite is green, iron ore is red. So why not? So that's basically what a spectrometer does. But it sees beyond the wavelength that we can see. No, it can see up and down the wavelength range. And this is what I'm showing here. So visible near infrared, our range is here, but our spectrometer can see different areas. And it's got a window of detection, so our spectrometer can see this window, and that window there, and that window in wavelength. Anything else it can't see. So if chlorite has a feature which is definitive, and it happens to be in this window, we can discriminate chlorite from other minerals. And that applies to iron oxides, etc. So we can do it at this scale. This is at CSIRO. It's like a flashlight. Just aim it at a rock like that. And you can't see it in the light very well, but here's the spectrum from it. And this is characteristic of iron-rich chlorite. So even though I can't look at a rock and I can see that it's chlorite, but I can't tell that it's iron-rich chlorite or iron poor chlorite. So that's the beauty of this method, is you can work out the presence of the mineral and also its chemistry. So you can do it with a flashlight, you can do it with an automated. This just scans entire drill core. They've got this out at Carlisle near the airport. GSWA, the survey, has. And you produce a continuous nice photo of the rocks. You also get the spectra, and then you interpret the minerals. So you can look at a spectrum, you can say, oh, that's chlorite. Okay, what's down the hole, 8 millimetres? Oh, that's chlorite. But the computer will do that for you, chlorite, 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 etc. So you get that for drill holes, and you can also get it from the satellite. There's the ASTER. I don't remember the acronym meaning, but it's a satellite that goes around the Earth, and it picks up what's reflected from the rocks. So what's beneath the rock is just the film. What you see is what you get. So it's not like any depth, but if there's outcrop, you'll get some information. So that's what I did with the project. This is a false colour image, so the range is here, that's banded iron formation. The red is actually vegetation, the other colours are false, it's artificial. But this is the data, the query data for iron oxides. So the banded iron formation is picked up nicely, and the mafic rocks are not. And we can do this from satellite. We can fly a plane over it and get better resolution, but the same sort of product at the end. And then you can integrate all of this. This is what I did with a project on iron ore. And here I'm showing chlorite, iron-rich chlorite. And I know my BIF is around here, and where I had the ore body was iron-rich chlorite. So this is a vector. This is a, go this way sort of tool. This is what we're looking for in exploration. And whizzing through laboratory studies, bulk rock geochemistry. Here's a rock, analyse it for its chemistry. Mineral analysis, there's a rock, there's a mineral from it. Look at its mineral chemistry. We can zap it with a laser. Fluid inclusion studies, we can heat rocks up and cool it down to negative 100 degrees and see different things. Stable isotopes, radiogenic isotopes, we can date things as well. I won't go through this in great detail, but the reason why we do it is we want to see what the signature of the ore body is. And remember, our veins are very narrow, our alteration is very large. So what's the chemistry of our alteration halo? And how is that different from the background concentrations? So that's why we collect the geochemistry to help us find the broader halos around the ore deposit. Fluid inclusions, I could have picked any study. I just had it here. I'm seeing what is the composition of the fluid. Go to your freezer tonight, pull out a ice block, hold up to light, you'll see these little inclusions trapped inside. That's essentially what's happening to these quartz veins. They're trapping these little inclusions. If you were to zap your ice block, it'd be recording the atmosphere in your fridge or your freezer. If you do that with the quartz, you're recording the properties of the fluid at the time that it crystallized a billion years ago. And if that quartz vein hosts gold, then that's what the fluid that precipitated these gold-bearing veins. It's amazing stuff. So, to conclude, geological mapping of outcrop and others provide the valuable data. It's very simple, it's cost-effective. It's high value, low risk sort of scenario. You can constrain what's controlling mineralisation. If you understand what's controlling the mineralisation, you can be predictive. I know that this type of fault is hosting the gold. Therefore, I'm going to look for that fault elsewhere. So that's being predictive. And I guess experience and common sense will help you work out what is important and how to apply these things. So I think that just take this on board, recognise what the key features are, and hopefully we'll see you in future years and you can actually apply this. Okay, any questions I'll wrap things up in terms of economic geology. It's a lot to sort of squeeze into just 2 sessions, but if anyone has any questions now they'd like to ask, go for it, or else I'll come down and see me as I wrap things up. Okay, thanks for your attention.